we're going to take a bit of a turn from what we've been working on this semester. You guys have been working a lot on multiplying polynomials, naming them, working with exponents. This unit is now going to take all that work we've done and apply it to graphing. So this unit is about graphing quadratics. Okay, so the first thing I want to do is define what a quadratic function is. Okay, and it has something to do with exponents, which is what we've been working with. So a quadratic function is a function that can be represented by the form f of x equals ax squared plus bx plus c. Okay, this is the general form of a quadratic function equation, and it's important to know that a, b, and c, what I've written right here, are values. I'm writing this a second time. I know I've gotten written here, but this is really critical that you recognize that a, b, and c are values. So, for example, a quadratic function could look like this: y equals 2x squared minus 3x plus 4. It could also look like y equals 2x squared minus 3. There's no middle term, there's no x term, but as long as I start with this x squared or have an x squared in it, that's the important part. So a quadratic function always has this x to the second power. Okay, and that's what I have written right here. The greatest exponent of the variable is x to the second power. You cannot have a quadratic function that has it to the third power. And you can't have a quadratic function that looks like this. If I have y equals 2x plus 3, this is not quadratic. In fact, we've worked a lot with this. This is y equals mx plus b. This is linear. So the two functions that we really work on in algebra is linear, which we spent all of first semester working on, and now we're going to start working on quadratics in this semester. Okay? Quadratics take a really special shape that you're going to see called a parabola. So anytime you graph something in this form, and you find points or put it in your calculator, it's always going to be this U shape. Okay? Or it could look like that as well. Okay? So let's define some things with this parabola, with this shape. Okay, there's some language we work with when we talk about a parabola. So the first part about a parabola that's important is this little point right here. Okay, we call this the vertex of a parabola, and it represents the turning point, the place where the curve goes from up to down or down to up. So that's called a vertex. Okay, I'm going to be asking you guys to identify that point a lot. Okay. The other thing that's important, just like in a line, is this point right here, okay? And notice that this is the point, and let me label these real quick to help you guys out. This is your y-axis, this is your x-axis. So the purple point that I just colored in, that cuts through the y-axis, so that is your y-intercept, okay? Even quadratics have y-intercepts, same as lines, okay? Two new, well, kind of new, not really, you've heard this before, but in quadratics, these 2 points are called x-intercepts. That's where this curve crosses the x-axis, right? So I'm going to highlight this curve a little bit here. So this is the curve. See how it crosses the x there, the y there, the vertex there, and then comes back and crosses the x-axis. So these 2 points are going to become really important later on, okay? Okay, so these points right here are called the x-intercepts. We also call these values a 0. And this is going to become important again later, that you can recognize that when I say, you know, locate the 0 of the parabola or the graph or the equation, that you recognize it's the x-intercept. It's just kind of a nickname for it, and I'll explain more of that later. The last part of a parabola is an invisible line. This blue line I've drawn in is not part of the graph itself. It's a little invisible line. And we call this the axis of symmetry. Now, the important part and cool part about a parabola is that any point you have, notice my 2 red points, it's equal distance to the axis of symmetry. Okay? If I have a point right here, I'm going to have another point an equal distance to the axis of symmetry. right? If I have a point here and a point here, it's equal distance to that line, right? It's like if you flip a piece of paper and cut it in half, you've got this mirror effect. And every parabola has this cool mirror effect. And that axis of symmetry shows the distance between the 2 points, okay? So this is your basic parabola and the most basic words we're going to use to be describing parabola. The last thing, I forgot, we have one more word to think about, and that is the shape of this graph. So see how these arrows are pointing down? We call a graph pointing down, a parabola pointing down, concave down, okay? So similarly with this graph is actually then called concave up. And the same thing applies here. This point is my y-intercept. I've got my 2 x-intercepts right here. I've got my vertex located right here at this turning point, the very bottom. And then I've got my axis of symmetry. Again, that axis of symmetry is invisible. I'm drawing it in to show you it's there, but it's not really part of the graph. It's just to help us plot points. Okay? All right, so let's talk about the most basic quadratic function we have, and that's actually y equals x squared. So this guy right here is important. Y equals x squared. It is it's called a parent function, right? Every other graph we create, or every other graph that we have, comes from this parent function, y equals x squared. And this is a function that we need to memorize. You need to memorize exactly how this graph looks and where the points are, okay? So we're going to start making a table for this graph, right? And when we make a table, we're plugging points in. So I've started with my x values, -3 to 3 over here. And what I'm going to do is I'm going to plug in these values to get a really basic set of points. So when I plug in -3, look, they've done it right here, they're actually squaring the -3. That's what y equals x squared means. It means take the x value, square it, and that's your y. So when we square -3, we get 9. So if we keep going down this list, if I do, I'm not going to put the y equals, but if I have -2 squared, that's going to give me 4. If I have the next point -1 squared, that gives me 1. 0 squared gives me 0, 1 squared gives me 1, 2 squared gives me 4, and 3 squared gives me 9. And if we take these points we've just found and set them as coordinates, -3, 9, -2, 4, -1, 1, 0, 0, oops, 1, 1, 2, 4, and 3, 9. These points right here form your parent function. Okay, and you'll notice something interesting about the parent in every parabola you ever graph. You've got this middle point right here, and then notice from the top and from the bottom, it's a mirror, right? 1, 1, 4, 4, 9, 9. They reflect each other. This is going to be true for every parabola you make, okay? You're going to have this really cool mirror effect. So when I plot this, okay, I'm going to first start with that 0, 0. Then I'm going to plot my negatives. So I'm going to plot this point right here, -1, 1. Then I'm going to plot this guy, -2, 4. And then this -3, 9 right here. Okay? Now, because the cool thing about a parabola, if I draw my axis of symmetry through the vertex right here, this point, let me do a different color so we can see a little better. Okay, so do you see how this point right here, the little red one, is 1 unit away? That means I'm going to have a point 1 unit away on the other side. Take a look at the second point. See how it's 2 units away from the axis of symmetry? That means there's going to be a point over here that's 2 units away. And same thing for this very top point. It's 3 units away, so the other points are going to be 3 units away. This is why the axis of symmetry is important. Okay, and if I check these values, I do get 1, 1, 2, 4, and 3, 9. So an axis of symmetry is very cool. It helps us graph points when we don't always have all 5 or 6 of them. Okay. Now when you connect these dots, it's going to form a curve and you're going to draw arrows on it. Okay, every time. So I'm going to put that here. Always use arrows when you plot your parabola. okay? Now, these values are really important, okay? What I've highlighted here, you have to memorize this pattern, right? You have a vertex, then it goes up 1 over 1, then it goes over 2 up 4, then it goes over 3 up 9. 1, 1, 2, 4, 3, 9. Okay, that is your parent function for parabolas, okay? So, when I describe this graph, I'm going to use this language down here, right? What's the vertex? The vertex is 0, 0. Axis of symmetry, that line that goes through the middle, when we write the axis of symmetry, we don't write a coordinate. You actually are going to pick the x value of the vertex. So there's my x value of the vertex. So when I write my axis of symmetry, I'm going to make it an equation x equals 0. Because remember, a vertical line always starts with x equals. We talked about that last semester. And then maximum or minimum, I'm talking about the vertex as well. Is this vertex the lowest point on the graph or the highest point? In this case, it's absolutely the lowest point, so it's a minimum. And this graph is concave up because it's pointing up. Okay, so this is the way I want us to describe quadratics, all right? So let's take a look at some other ways that we transform from the parent. So look at these two equations. In this first one, I have the parent, but then I'm also having this 2 in front. This one I have the parent, but now I've got a 1/2 in front. So really what you're saying is you're saying, hey, look, I've got the parent function, now multiply that by 2. So I'm going to go ahead and list my parent function values out, which I know are 941, 0, 1, 4, 9 when I start with -3. So these are my values at -3, -2, -1, etc., right? So if I'm multiplying everything by 2, 9 times 2 is 18. So when x is -3, this is 18. 4 times 2 is 8. 1 times 2 is 2. 0 times 0 is 0. 1 times 2 is 2. 4 times 2, sorry, this should be a 2. 4 times 2 is 8, and 9 times 2 is 18. Okay? Now, if this is too confusing, and I get for a lot of you it is confusing, I do want you to understand that you're basically taking the parent function and you're doubling it here, or in this example, you're taking the parent function and multiplying it by 1/2. But if getting these values is challenging for you and thinking of this 2 times thing, I really want us to learn how to use the calculators. So, right here, I want us to, on your paper, I know you've got space for it, right underneath this graph, I want you to list some steps for the calculator, okay? Okay, alright, so, let's take a look at our calculator. Alright, step 1, of course, turn your calculator on, alright? Alright, so, you've got this blank screen right here. The first thing you're going to do, and I'll put it on here, is you're going to press the y equals button. Okay, it looks like this, and it's right here in that upper left corner. So hit y equals, okay. Clear out, if there's an equation there, hit the clear button. Clear it out so you get this big list of y and numbers, okay. The second step then is to type in the equation. So, in this case, my equation is this guy, this y equals 2x squared. So I'm not going to put the y equals in my calculator because the y equals is already there. I'm just going to type in 2x squared. So I'm going to hit 2, and then I'm going to hit this variable button. See this xt circle n? That gives me an x when I hit it. Then I'm going to hit this little x squared button right there, and it will give me the exponent x squared. Okay? Now once I've typed in the equation, I can hit graph. Okay, so I'm going to hit the graph button. And what this does is it's going to show a little sketch of what the graph looks like. See how it's a U shape, it's a parabola? It's going to show you a picture. Now what you do not do is then go, hey look, there's the picture, all right, my graph looks like this and I'm done. That is not okay. Okay, to graph a quadratic function or any function, you need at least 5 points to graph. Always. So I want coordinates like I put in the table here. So to get the coordinates, you're going to hit the second button. The second button, that's yellow. It's right here. Hit second and a little arrow will pop up there. And then you're going to hit the graph button again. So I'm going to hit graph. And look how a table pops up, okay? And you'll notice it matches my table. See how I've got this table here? Do you see how it matches the table I've created? So if creating the table is the challenge for you and you don't want to do it in your head or by hand, I get that. You've got this awesome tool here to help you do that. Okay, so that's really critical that you have your graphing calculator. Otherwise, if you can't create these points, you're going to really struggle this whole unit. Okay, so that's how we get this on the calculator. All right, so let's go back to our graph and let's plot some of these points. All right, so I've got 0, 0 right there. So I'm going to plot that here, 0, 0. Then I've got negative 1, 2 here, 1, 2 here, and then I've got 2, 8, and I've got negative 2, 8. I'm not going to graph the 18 because it kind of goes off the grid, and then all I have to do is connect these points. Okay? Easy peasy. All right, now we've got this another function here. All right, it's 1/2 now. So now we're working with this a being 1/2, right? That's a 1/2 right there in front. So let's go to our calculator and type that in. Now to type in, we're going to go back to our y equals. My old equation's in there, so I'm going to clear it out by hitting clear. Now to type in a fraction, I'm going to hit parentheses, and then whatever the fraction is, this is 1/2, so I'm going to hit 1, the division symbol, 2, and then parentheses, and then my x, and then my squared. So there's my x button right there, and then my squared button right there, and I've put in the equation. I hit graph to see the picture of it. Notice that this is much wider than the other parabola, right? This is going to become kind of important. This guy got a little wide. Let's take a look at the points to make a table. I'm going to hit second, and I'm going to hit table. And notice with this graph, it's giving me the vertex right there. I can tell it's the vertex because it's like right in the middle and then it starts to mirror out. So I've got 0, 0, and then I've got negative 1, 0.5, negative 2, 2, and negative 3, 4.5. And then this is just mirrored, 0.5 to 4.5. All right, so I've got my table. Now let's plot these points. Okay, I'm going to erase some of this stuff here just so we can get a clearer picture. Okay, all right, now I'm going to plot. I've got 0, 0, I've got negative 1, and then I'm estimating that 0.5. So I've put it in between the lines, that's 0.5. For some of these graphs, you will have to estimate. They're not always perfectly on the grid. And then I've got negative 2, 2, and 2, 2 here. And then this is all the points I need. I need at least 5. But I'm going to go ahead and graph the 4.5 because I can. It's on the grid. And then I'm just going to connect the dot points here. Okay. Now remember that your parent function looks like this, right? Y equals ax squared. That's your parent right there. Okay. So in this case, I've got a equaling 2, and I've got a equaling 1/2. Well, the 2 made it skinnier, right? This made it skinny. And this 1/2 made it wider. So we can kind of create a little rule for ourselves when we're thinking about a. Okay, and now here's the rule. When a is greater than 0, or a is less than 0, meaning like if we have negative 3 or negative 4, it gets skinnier. And we have a name for this. We call this a shrink. We're saying the graph shrinks. On the other hand, when a, and this is kind of weird to think about, when a is a fraction between 0 and 1, it gets wider. Like you can see above, right? Do you see how a is a fraction, 1/2 is between 0 and 1? And we call this a stretch. Okay? Shrinking and stretching. If a is big, like 2, 3, 4, it's going to shrink. And if it goes negative 2, negative 3, negative 4, it will also shrink. If you have a fraction like 1/2, 3/4, 5, like 2/5, it's going to get very wide. Okay? Okay. Now let's talk about what happens when a is negative. So these last couple examples, notice the 2 and the 1/2 were positive, and these graphs went up. When a is negative, it changes a little bit. So now I've got the equation y equals negative x squared, okay? And so I'm going to go ahead and use my calculator to put these in a table, right? So I'm going to type in y equals, clear it out, negative x squared, and I'm going to graph it. And when I graph this, look how the graph changes. It goes down. That's what a negative does. It makes the graph go down. So I'm going to get my table, second table, and now all of my y values are negative. So instead of 9410149, I now have negative 9, negative 4, negative 1, and then still negative going back. Okay, so that's what a negative does. It makes it go down into the negatives, right? So when I plot this, I'm going to have the vertex is still at 0, 0, and then again, it's always the over 1, down 1, over 1, down 1, over 2, down 4, over 2, down 4, and over 3, down 9 for our parent function. See how there's no number here, it's just a sign? Parent function always has that same pattern of 9410149, okay? So this is now flipped over, basically. We flipped the graph on the other side of the x-axis. The vertex is still the same for now. My axis of symmetry is still going through the middle like that, right? Now, though, this vertex is no longer a minimum. That vertex is the maximum part of the graph. So that vertex is the very top point, and we call this something concave down, okay? So when A is positive, it's going to be concave up, and when A is negative, it's going to be concave down, okay? We still have stretching and shrinking, though, with that A value, right? So let's look at these two other examples. Now I've got a negative 3 and a negative 1/3, and we're still going to see that stretching and shrinking of our shape, okay? So if I go to my graph and put in negative 3x squared, I'm going to go back to y, I'm going to put in negative 3x squared, and I'm going to graph it. Notice now it's a lot skinnier. See how it kind of shrank, it got skinny? And if I hit my table, there's my vertex at 0, 0, so I'm going to go ahead and put that in. And now I've got values of negative 3, negative 12, and negative 27 on either side. Okay, so now when I go to graph this, I'm going to plot this guy first, the vertex, and then I'm going to plot the negative 1, negative 3 on either side. So those are these 2 points right here. Now negative 12, I need 5 points, right? Negative 12 kind of goes off the grid. So in this case, because my grid's not big enough, I'm going to go ahead and estimate these to be about like right here-ish. Okay, so this is an estimate, but I'm still getting the point across here that this graph is much skinnier than my first one. And it's skinnier because A is less than 1, right? It's a 3, it's anything like that, 2, 3, 4, 5, negative 2, 3, 4, 5, that's going to be a shrink. On the other hand, this guy, when I type it into my calculator, negative 1/3 x, let's clear this out and try this one. I'm going to put this in parentheses, negative parentheses 1 divided by 3 parentheses x squared. When I graph this, it still points down because it's negative, but look how much wider it is with that fraction. Okay, so when I get my table to make the points perfect, I see my vertex, oops, sorry about that. I see my vertex is still at 0, 0, but now I've got some decimals, right? Decimals are okay, right? We're going to practice estimating decimals. This says negative 1, negative 0.3, and then negative 2, negative 1.3, and negative 3, negative 3. So these are the points we have to plot, and we're going to go ahead and estimate those. Okay. So I'm going to start with my 0, 0, and I'm going to go ahead and use colors for this. So here's 0, 0 in red. The next point is negative 1, negative 3, negative 0.3. So I'm going to do negative 1, and negative 0.3 is about right there on either side. That's about 1/3. And then for the next point, I've got negative 2, negative 1.3, and that's about right here. All right, and then finally, negative 3, negative 3, I can graph that one, right? Negative 3, negative 3. Do you see how much wider this is? Okay, that's what the fraction does to the graph. It makes it wider, okay? So the final conclusion here, in all quadratic functions, this leading coefficient a determines whether it's concave up or concave down, and it determines a shrink or a stretch. Okay? All right, now I want you to pause this video and take like a 5-minute break. I've still got 2 other things to do in this learning target, and keep in mind this unit, the videos are going to be much longer. There's a lot more stuff we have to talk about and I have to explain to you. So go ahead and pause, take a break, get a drink of water, and then come back. And then we're going to work on the last thing for this learning target, all right? All right, one of the last things we also need to be able to do with the parent function is create the equation from the graph, okay? So let's say I give you this graph right here. This is a parabola, it goes to the vertex at 0, 0, and it's at the point 2, 2. So to do this, I'm first going to label 2 with an x and this other 2 as a y. Okay? And I'm going to write down my parent function, y equals ax squared. Okay? So this 2 is x, this 2 is y. Here's my parent function right here, y equals ax squared. I'm going to replace x and y with the coordinates. Okay? So here are my coordinates. I've got the 2 and the 2. So when I rewrite this equation, instead of y equals ax squared, I'm going to put 2 equals a2 squared. I'm plugging in for x and y, 2 and 2. Okay? Now I can just simplify this and solve. Bring down the 2. A times 2 squared is a times 4, which is the same thing as saying 4a. And then divide both sides by 4 to get a equals 1/2. Now that I know a equals 1/2, I can write my equation as y equals 1/2 x squared. Okay? Pretty simple. We can only do this when we have the vertex at 0, 0, though. Otherwise, it doesn't work. But we're going to use that for now. So on this next one, I'm going to do the same thing. I'm going to label, here's my parabola, and here are my points, x and y. Okay? I'm going to start off with my parent, y equals ax squared. And then I'm going to plug in for x and y, -2 and -8. So y is -8. I'm going to keep the a, parentheses, plug in -2 for x. All right? Now I'm going to evaluate this, bring down the -8. -2 squared is 4, so I get a times 4, which is the same thing as 4a. Divide by both sides by 4 to get a alone, and I get a equals -2. And when I put that back into my parent, I'm going to leave my y and x and just put -2 in for a to get that equation. All right? And it kind of makes sense because when I look at this right here, I see a negative sign, and that makes sense. It was negative, and the 2 means it kind of shrinks a little bit. Here, I've got a 1/2, and it's positive, and look how wide this graph is, and it's concave up, which matches positive. So it kind of my answer kind of makes sense. Okay? Go ahead and pause again and try and do these 2 on your own. You're starting each with the parent. I'll write that out for you. And then you're going to go ahead and plug that point into your x and y and simplify the same way I did. Okay? So take like 2-3 minutes and try them on your own to get the equation. For the first one, you should have gotten y equals 4x squared. And for the second one, you should have gotten y equals -x squared. Okay? If you're struggling on this, come talk to me. We'll do it together. Okay? And finally, the last thing that we need to be able to do is just look at a graph, look at a situation, and just describe what's going on. There's no math here, really. I just want you guys to be able to describe what's happening, okay? So in this graph, you're modeling a dolphin, and he's under the water. He's going up from the bottom of the water to the top to breathe, and then going back down again. So when I picture this graph, I think, okay, this is water. There's the water. And the dolphin is underneath the water and heats air. So we can show this by showing his increase to the surface, decrease to the surface. But my question is, what does all this numbers mean, right? So the vertex, that vertex, what does that mean? In this problem, it means that is the point where he reached the surface, or she, could be a lady dolphin. All right. How about the 2 endpoints, right? How about this point and this point, right? Those 2 points both have the same numbers, just the 4 is negative and this 4 is positive. So what this is saying is it's saying it takes him 4 seconds to reach a depth of 32 feet. Because here he's starting at 32, and then he's swimming, 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 swimming. After 4 seconds, he reaches the top. Then he goes back down, and after 4 seconds, he goes down 32 feet. Okay, so that's what those two things are saying. All right? This is kind of what I just generally want you guys to be able to do. And if we wanted to determine the equation of this, we do it the same way. I would start off with, this is what this says, determine the function that describes this plot. So I'd start off with my parent. I'd plug in one of these points, it doesn't matter which one. Let's do negative 32 equals, and then we'll plug in the 4. I get negative 32 equals 16a. Divide both sides by 16. I get a equals negative 2. So my equation is negative 2x squared for this dolphin. Okay? I know this is a lot to start a unit. This unit is... There's a lot happening in this unit. So this is one of those things where if we don't get the basics here at learning target 1, then the next few learning targets are going to be really a struggle. So take this learning target really seriously. Try to really grasp the shrinks and the stretches. Try to grasp how if it's negative, it flips. That's the kind of thing I want you thinking about here in this learning target. Okay? Good luck on the practice. Thank you for your patience listening. You guys are great, and I look forward to seeing you in class.